Welcome to another episode of Terry's Notes. Today we are going to be looking at different types of structures. The first type of structure we're going to look at is the structure of a metal. A metal crystal consists of positive metal ions held together by a sea of negative electrons. There are strong bonds between the sea of negative electrons and the positive metal ions. The valential electrons of each metal atom are delocalized, meaning that they are free to move throughout the structure. So if you look at this diagram, let's say we use sodium as an example. We will have sodium will produce sodium ions plus one electron. So the positive ions in this case would be sodium, and these red dots represent the free electrons. So each sodium atom produces one sodium ion and one electron, and these electrons are free to move throughout the structure. And it is this sea of electrons that bonds, or there's an attraction between the sea of electrons and the positive ions, and this is called metallic bonding. Let us now look at the physical properties of metals. Metals have high melting and high boiling points, and the reason for this is there are strong metallic bonds present between the positive metal ions and the sea of electrons. A large amount of energy is required to break the metallic bonds, and it is for this reason that metals have high melting and high boiling points. The second physical property, they conduct electricity. There are free mobile electrons within the structure, and since the electrons can move, the metal is able to conduct electricity. Metals also conduct heat, and this also has to do with the free mobile electrons. The free mobile electrons transmit energy in the form of kinetic energy. So if one end of a metal is heated, the electrons gain kinetic energy and they begin to move around the structure. When they collide with the positive metal ions, they give up some of this energy, and what is happening is that the vibrations move throughout the structure. And remember that the temperature of an object is proportional to the kinetic energy of the molecules or the particles that make up the object. The fourth physical property is that metals are malleable and ductile. Malleable meaning that they are bendable, they can be reshaped, and ductile meaning that they can be stretched into a wire. And the reason for this is that the positive metal ions are able to slip over each other, and the sea of electrons is still able to keep the metallic structure together. Now let's look at some allotropes. Allotropes are different structural forms of the same element in the same physical state. You need to be able to give a definition for an allotrope. Diamond and graphite are allotropes of carbon, and they are both macromolecular crystals. Now let us look at the structure of graphite. Each carbon atom is bonded to 3 other carbon atoms. So for example, if we were to look at this carbon atom, we have 1, 2, 3 carbon bonded to this carbon here. Carbon has 4 electrons in its outer shell. This means that there is one free mobile electron for each carbon atom. The electron is not localized to a single carbon atom. The electrons are delocalized, meaning that they are free to move throughout the structure. The bond between each carbon atom is covalent and very strong. So what we are saying is that between a carbon and a carbon, there is a strong covalent bond here. So let's say this carbon and this carbon, this represents a covalent bond, and it is very strong. The structure consists of hexagonal rings which form layers. So we have one layer being shown here, and we have a second layer being shown here, and the bond between the layers are very weak. So these dashed lines represent the weak bonds between the layers, and these bonds are referred to as van der Waals forces. Now let us look at the physical properties of graphite. Graphite is soft and flaky, and the reason for this is that there are weak intermolecular forces between the hexagonal layers. Graphite has lubricating properties, and the reason for this is that there are weak intermolecular forces between the hexagonal layers. The layers are able to slide past each other. The third physical property, graphite has a high melting point. Covalent bonds are strong and require a large amount of energy to break. Now some students get confused with this. Covalent bonds are strong bonds, and they do require a large amount of energy to break. Fourth physical property, graphite conducts electricity. Now carbon has 4 valence shell electrons, and 3 of them are used in bonding. Therefore, you have 1 free electron for each carbon atom, and these free electrons are delocalized, meaning that they can move throughout the structure. And this is the reason why graphite is able to conduct electricity. Now graphite is used in the manufacture of aluminium in the electrolysis process. It is used as an electrode. It is also used in electric cells, and it is also used in lubricating liquids. And it's used in lubricating liquids because of its lubricating abilities, and it is used as electrodes because of its electrical properties. Let us now look at the structure of diamond. Each carbon atom is bonded to 4 other carbon atoms. So if we look at this carbon atom here, we have 1, 2, 3, 4 carbon atoms. So all the valence shell electrons are used for bonding. There are no free mobile electrons. A carbon atom has 4 electrons, 4 carbon atoms arranged in a tetrahedron around itself. So when we say a tetrahedron, we're talking about this shape here. Let's say these 4 here. So you would have had the central carbon atom. We draw another one. We'll draw one in the same plane. Then you'll have another carbon atom that is behind the plane of the paper. And then we have another carbon atom. So this shape that you get here, it's called a tetrahedron. So that's why we say the carbon atom has 4 carbon atoms arranged in a tetrahedron around it. The bond between the carbon atoms is covalent and is strong. So what we're saying is that if we look at, let's say, these 2 carbon atoms here, this bond is a covalent bond and it is very strong. Let us now look at the physical properties of diamond. The first physical property is that diamond has a high melting point. Diamond is a macromolecule. The covalent bonds are strong and require a large amount of energy to break, and this is why it has a high melting point. The second physical property is that diamond is extremely hard. The strong covalent bonds exist throughout this giant structure. And this is what makes diamond so hard. Third physical property, diamond does not conduct electricity. All 4 valence shell electrons around each carbon atom are used for bonding. There are no free electrons. The uses of diamond. Diamond is used in drill bits, and it is used in cutting tools because diamond is very hard, and it is also used in jewelry. Let us now look at an ionic crystal, for example, sodium chloride. Each sodium ion is surrounded by 6 chloride ions. So if we take this as being one sodium ion, we have 1 chloride ion, we have 2, we have 3, 4, 5, and 6. Right? The dark circles represent the sodium ion, and the white ones represent the chloride ions. Sodium chloride is a crystalline solid, and the crystal is cubic. There are very strong electrostatic forces between the sodium ions and the chloride ions. Now let us look at the physical properties of sodium chloride now. Sodium chloride has a high melting point. And the reason for this is that there are strong electrostatic forces or ionic bonds that exist between the sodium and the chloride ions. And therefore, a large amount of energy is required to separate the ions. And that is why it has a high melting point. Sodium chloride conducts electricity when molten or dissolved in water. When it is molten, the sodium and chloride ions become mobile. That is, the positive and negative ions move under the influence of an electric field. So for example, if we have an electric circuit, and we have a container with sodium chloride crystals. If we use solid sodium chloride, we will not get a current to flow in the circuit. If we begin to heat the sodium chloride until it melts, then we get an electric current because the sodium and chloride ions become mobile. If we dissolve the sodium chloride in water, the ions also become mobile. The positive and negative ions move under the influence of an electric field as well. And the third property is that sodium chloride is soluble in water. Water is a polar solvent, and sodium chloride is made up of ions. So bonds are formed between the ions and the polar water molecules. Let us now look at the structure of simple molecular crystals. And the example we will be using is iodine. Now, iodine exists as I2, which means that we have 2 iodine atoms joined together by a covalent bond. Now, iodine is a simple molecular crystal. An iodine molecule consists of 2 iodine atoms covalently bonded together. The covalent bonds, or what we call the intramolecular bonds, are strong. The bonds between the iodine molecules, or the intermolecular bonds, are weak. And the melting point of iodine is low because of the weak intermolecular forces. Now, this is something that you need to pay attention to. This represents an iodine molecule. This is another iodine molecule. This is one here as well. This is another one here. Now, the bonding between the iodine atoms is covalent, and this is very strong. But between the molecules, that is these dotted lines here, these bonds are very weak. And it is because these bonds are very weak that iodine has a low melting point. It is able to convert into a vapor very easily.